On bonding for you guys, so you should be on page 42. Your essential question is, how do ionic bonds form? And then the topic today is ionic bonds. So if you guys are ready, I'm all set. Are you guys all ready? Perfect. That is the correct answer. Okay. So we are starting off then with why and how chemical bonds form. So it begins with this phrase that we've got here. Can you guys see it all right with the glare back there, Lucas?
Yeah.
Oh, thank you. You can see it all right? Okay. So the first phrase we'll start with is atomic stability. And if you think about stability, we won't even need to define it here, but just think about stability in terms of your own life or in terms of what's going on. And not the definition of stability, but what does it mean when you are stable?
You don't fall over.
We'll go with hands. Gage? Okay. I'm with you. Okay. Okay. Would you say, can we kind of say it like this? If you're stable, if you're like comfortable, stable, in control, that means that things maybe going on around you don't have a huge impact. Like you're just kind of sailing your own course. And you're not. So atoms are somewhat similar to that, in that atoms can be stable, which means that they do their own thing. They're not influenced by the other things around them. Or atoms can be unstable. And most of the atoms on the periodic table, in fact, almost all of them, are unstable. So here's the weirdest part about it, is atoms, even though they're atoms, they recognize that they're unstable. And just like a person who recognizes that they're unstable, they seek help to become stable, whatever that help might be. Atoms do the same thing. So what it means, though, for an atom not to be stable is it means this, that they do not have a full valence shell of electrons. If an atom has a full shell, like its whole outer shell is full of electrons, it's totally stable. If it's not full, totally not stable. There is only one group of elements on the periodic table that has a full shell, one family. What's the name of the family, with a hand, what's the name of the family that has a full shell of electrons? Chris? It is the noble gases, all the way on the right-hand side. With another hand, most of those noble gases have how many electrons in their outer ring? Cool? I'll go with someone else. Kedra? 8. There's only one of them that does not have 8 in its outer shell. With a hand, what is the name of the one element that doesn't fit 8 in its outer shell? Rylan? Helium's the one. Very good. So helium is the one. So for every element on the periodic table that's not in that row right there, from helium all the way down to radon, everything that's not there, that means everything to the left of it, is unstable. Will react with other atoms and is potentially can form bonds.
Is it,
That's all right.
is it not a full valence shell?
Yep.
Okay.
Just valence shell is what we're talking about. When it comes, hey Damaris, thank you. When it comes to bonding, the only thing that matters, not protons, not neutrons, just the electrons in the outer shell, just valence electrons is all we're talking about with bonding. So, next part, which is kind of a restatement of it, just the same thing on the top as it is on bottom, just in different words, if you want in different words. Unstable atoms do not have full valence shells. They don't have a full outer shell. That's what it means when they're not stable. If they're, maybe you know some unstable people in your life, and they are reactive. Like little things, little situations that they come around induce like big responses sometimes. People that are stable, little things they come in contact with their life, they're able just to keep going and it doesn't really affect them. Unstable atoms, when they come in contact with other unstable atoms, react. There is a reaction that takes place. What's that? We'll talk about it in just a second. So, next piece here is that unstable atoms, right, those are atoms that don't have a full shell, form bonds really easily. And we'll talk about what a bond is here in a second. But they form bonds really easily, and the things that they when they form bonds are called compounds. Like salt. Yeah. So here's a question for you as you're sitting there finishing this up. If having a full valence shell makes you stable, things that form bonds are doing so to make their valence shell full, to make their outer layer of electrons full. And you should have got this from what you did online Friday. There are 3 ways that an atom can go about making its valence shell totally full. I'll take any one of those 3 ways. What are the 3 ways atoms can fill up their valence shell? Lincoln? There's one. It can lose an electron. We'll talk about that in a second here. Jasmine? It can gain an electron. Or it can do what they do in covalent bonds, and that is, Lucas? They can share electrons, which is this next piece that's here. So to gain stability, to make it so they are stable so they're not reactive anymore, they form compounds, and they do that by losing, gaining, or sharing electrons. And not just any electrons, but valence electrons in their outer shell. And it's the goal of all these things to be stable. So I did my best drawing these circles around here. But as you look at it, can you tell what element it is? It's really hard to see. Yeah. 1, 2, 3, 4, 5, 6, 7. Yeah, there's a sneaky one right there. So as you look at this, and you look at the whole thing, would you be able to tell, just by looking at that picture, if that thing is stable or unstable? I know, that's because my circle isn't great, but you're going to have to imagine this out here. Is that a stable atom or an unstable atom? What tells you that it's stable? Nope, so let's go back. No problem. Lincoln? Stable or unstable?
Stable.
Okay, how do you know?
Because it has the same amount of electrons as it does protons.
Okay, Chris Owens, a differing opinion?
It's unstable because it's not a noble gas and it doesn't have a full outer shell.
So he gave us nice job, Chris, 2 pieces of evidence there for it. It's not stable because, number 1, he said it's not a noble gas, it's nitrogen, and we know anything that's not a noble gas is unstable. And number 2, is its outer shell full? No, it takes 8 to be full, right? So nice 2 pieces of evidence, Chris. I like that. Good job. So we know that this thing we think is nitrogen unless there's another yellow one hiding out back there, and it's unstable. Could we make nitrogen stable? Yeah, you plug in a couple of electrons out here and it becomes stable, right? And we'll talk about how that happens and what happens when that does happen. So next piece is this. It's basically the definition of the word chemical bond. And that is when atoms do share electrons, they form a chemical bond. And a chemical bond is just a force that holds atoms together in a compound. So it's like Chris brought up salt earlier, which is sodium chloride. And it's the force that holds the sodium atom to the chlorine atom. And that's the thing that keeps them together, locked together like supermagnets or something like that. And on this slide, you can see some different combined elements that we'll talk about here. These are all naturally occurring things that you can find in places, and we'll talk about what they are and what the numbers mean. So if you can see this down here, can you see the H2? Okay, what's the H mean? And what's the number 2 mean? 2 of them, right? So H2 means that literally there are 2 things of hydrogen. It's like chemical shorthand for the formula for stuff. You know how in a cookbook it might tell you like 2C of sugar, 2 cups of sugar or whatever, or 3 cups of flour? This is just telling you it's 2 atoms of hydrogen is all that's telling you. So when you see these numbers and letters up here, read it like a cookbook. It's telling you what the ingredients are to make that particular thing. Like you guys know the recipe to make water, correct? H2O, right? You probably knew that, but it's H2O. And you can see that up here. I'll get to you, Lincoln. Hold on just a sec. So we've got other things up here. Hydrogen gas. Do you know the story of the Hindenburg?
Yeah.
That's the Zeppelin that was full of hydrogen gas and the spark caused it to blow up. So super flammable, right? Oxygen's the same way. That's why you can't smoke in hospitals, because oxygen's flammable, and if it's exposed to a flame, it will blow up. Because some people just aren't that. So nitrogen is about, I think it's 78% of our atmosphere. So when you take a breath in, you breathe in 78% nitrogen, and then you breathe it back out. Doesn't do you any good. Doesn't do you any harm that we know of. And then chlorine gas, that's here, that's a poisonous gas. So take a breath of that. Can you guys ease off on the side conversations, please? Thank you. So chlorine gas, like I said, poisonous gas that you got. We take a look down here, though, and things get different on this side. And that is because of what we'll talk about here in a second. These are compounds. They're two elements that are combined, and they have different properties than the elements that make them up. And the easiest one to show is with water. Hydrogen flammable, right? Yeah. Oxygen flammable. You would assume that if you put hydrogen and oxygen together, a flammable substance plus a flammable substance, you'd make a really flammable substance. But in fact, when you put hydrogen and oxygen together, you make a thing that puts out flames. So they don't have the same properties that they did on their own back here. They've got a whole new set of properties, right? Because hydrogen's a gas, oxygen's a gas. You put them together, they make a liquid. NO2, this stuff, if you've ever been to the dentist and had laughing gas, that's what it is. Yeah. So this one, you don't need to write anything down until we read it and explain it, because chances are most of you guys know this already. So if I asked you this, without looking at this, because we kind of did this already, if you look down at the bottom here, we've got, hey Taylor, now all those things are examples of this fact, that compounds, and these are compounds because it's two or more elements put together, do not have the same properties of the elements that make it up. So when two atoms bond together, the thing they result in does not have the same chemical or physical properties of the things that make them up. Now, earlier you had a question, Lincoln.
What makes a mixture?
A mixture is, so typically it's seen as, like this would be if you mix different substances together, I think is what I'm trying to shoot for there.
Elements, compounds, and mixtures.
Yeah, so compounds and elements are bonded together at like the atomic level. Mixtures are just like you take peanuts and M&Ms and stir them together, and you got a bag of peanuts and M&Ms mixed together. Right. They're not chemically adhered to each other. Gage?
Would that also come according to the other concept that with that bonding, with that kind of goes that kind of bonding?
Yep.
You know what I mean?
Was that in your way?
No.
Yeah.
Okay. So the other example we can bring up is the one Chris brought up earlier, which is salt. And if you remember when we went over the periodic table, salt is in the alkali metals group. Do you remember what happens with an alkali metal when it's placed in water? It explodes, right? And chlorine, like we mentioned, is a poisonous gas. Take a breath of that and it's over for you. But you combine those two things, a metal that explodes or catches on fire or sizzles or decomposes, whatever you, or it doesn't decompose, but it bonds. When you put it in water violently and a poisonous gas, put them together and you make something that you need to live. If you don't have salt, you don't live. But how ironic that where you just swallow just sodium, that'd be an issue for you. And if you were to breathe in chlorine, that'd be an issue for you. But when they're combined, you absolutely need them. They're critical for you to live. Yeah, you get high blood pressure and stuff like that, but it doesn't blow up inside you. I was saying, you don't have to write this down if you can answer this part correctly. If you look at the bottom and you know what this means, H2O, what's the H stand for? All right, and the 2 tells you, okay, and the O, last piece? All right, so you get the water part. You get it, right? We said that's like a recipe. If you look at this next part, H2SO4. Number one, do you know what H2SO4 is?
No.
2 hydrogen, 1 sodium, and 4 oxygen.
We were asking what it was.
It means sulfur.
Yeah, so Lincoln is totally right. It's 2 hydrogens, a sulfur, and 4 oxygens, but you don't know what the name of it is, right? Yeah, okay. Not a big deal. We can figure that stuff out. But what the point I was trying to make is if you know if you know how to read these recipes that are down here, H2SO4, you don't have to worry about what I wrote here. This is a chemical formula, and all it does is tell you what atoms are in it and how many of each one there are.
Okay.
Make sense?
Yeah.
So most of you guys, like I suspected, knew that already. If you didn't know that, you want to get this down. You want to be able to explain this. But if you knew how to do that already, you're good. Good with this slide? Okay, I'll give you a second. Because up next are 3 questions for you that you guys will do in your group here.
Wait, are we writing these questions in the book?
No. You're going to read them, talk about them as a group, and be ready to give one coherent answer to 3 different questions.
One answer for 3 questions.
One answer for each of the 3 questions. My thing has, it's probably low battery. Yeah. Down, but it's more of an explanation here. It would be super helpful if you guys had your periodic table on your spot. If you don't, you can certainly look at that one up there. But it's going to make it really easy if you've got yours, because we're going to add some numbers to it here in a little bit.
Because I had to do cornrows and makers, and then you were gone, so...
Okay, give it to me at the end here when we're done with notes. I'll take it from you. All right, so now that either you or someone you can look at that's close by has their periodic table of information out, we can go through some of these questions with focus, right, Jason? Thank you. So, as we take a look at this, I need you guys to find potassium on there. It's number 19. And I want you to answer the question within your group, and then you can give it to me. But I want you guys to agree on it before you tell it to me. How many valence electrons does potassium have? So in your group first, and then I can get an answer from you. Yep. So 10 seconds. All right, so with your folks back up here, please. We want the solution to that. Cody Chartrand, how many valence electrons does it have, Cody? 1. How do you know it's 1? All right, so if you remember, as a quick refresher, if it's in that first column, it's got 1 valence electron, correct? That's how you tell. So if we were to draw potassium, it has 1 in its outer shell, right? If you find on your periodic table, I think it's number 53, iodine. Can you find iodine on there? So as you find that, how many valence electrons, this time we can just get a number, how many trinity does iodine have? 7. Okay. So can we be in agreement that neither potassium or iodine are stable elements? All right. Daisy, can you tell me why neither of those things are stable? Yeah, their outer shells aren't full. They're unstable like we talked about. So because they're unstable, are they going to form bonds or not form bonds? Chris?
They're going to form bonds because 7 plus 1 equals 8.
All right, they're going to form bonds. I appreciate the monotone voice. That's great. So they will form bonds.
Yes, they will.
So they're going to form bonds because neither one of them is stable. If they're not stable, they form bonds. So let's take a look at what this looks like when they do here. If we did this, so I'm just going to draw the outer layer of potassium. Well, I can draw the whole thing. So if that's our nucleus of potassium, how many layers of electrons would it have? 4, because it's in the 4th period. And we go outside in. We already discussed that it has 1 electron on the outside. Every other layer under that should be totally full. So 2, 4, 6, 8. 2, 4, 6, 8, and 2 on the inner layer like that. So this thing has a choice here. Because to get stable, it needs a full outer shell. And to have a full outer shell, it needs a full outer shell. So it's got 2 ways to do that. It can either gain 7 more electrons around its edge here, or it can lose an electron. If everything's equal, if gaining an electron is just as hard as losing an electron, is it going to be easier for this thing to gain 7 electrons or to lose 1? Easier to lose 1. And if we did that, so I'm doing it up here to show you, if we lose 1 electron from that outer layer, would you agree the layer left is totally full? Yeah, now it's stable, right, when it's done that? But something has happened. So in your group here, in about 30 seconds, if you could, can you tell me what has happened to the charge of this atom in your group, not out loud, or not yell it out, but in your group, what's happened to the charge of that atom since it lost one electron on the outside?
Good question.
Only two choices, right?
Yes.
So it loses one, so that means it's... Is an electron positive or negative?
It's negative.
Okay, so if you lose a negative...
It would be positive. Oh, that's right.
Yeah, so think about humans, right? If you lose your negativity, you become positive.
It's like mathematics. Too close.
You guys got a solution?
Yeah, it's positive.
Okay.
We're too close.
All right, so let's bring your focus back to here, please. And this question's going to Ashlyn, who gave me the thumbs up, like, yeah, I got it. You ready for this, Ashlyn? Perfect. Hunter, thank you. So the question was, Ashlyn, this thing lost an electron which does something to it. I'll give you a hint, it does something to its charge. What happened to the charge of this thing? Very good. It lost a negative, so this becomes positive like that. So we're doing well there. If we take a look at iodine, how many did iodine have in its valence shell? 7. Is it going to be, without drawing it out, is it going to be easier for iodine to gain 1 or to lose 7? If it gains an electron, what charge will it have? A negative, right? And that's what somebody was talking about at the start. These things are like magnets a little bit, where we've got one that's positive and one that's negative, and it's like that saying in dating, right? What's the saying in dating about opposites? Opposites attract. The same's true here. The positive charge of this attracts the negative charge of that, and they wind up getting stuck together in a bond. That's how that works out. That's what causes the ionic bonds that we're working with today. So what I'm going to go through here with you is this. We're going to come up with how the 4 steps to write out formulas like H2O and CO2, like how to come up with those, because they're not random. There's an actual way. Right, Rylan? Okay, can you stop making, I don't know what, highlighter skyscraper system? Please. All right, so last thing we're going to get in there today is this, is how to write these formulas out. This is the last little bit we've got. So this one, somewhere in your Cornell notes, you want to set it aside kind of on its own, because this is something that you want to be able to refer back to easily. So you could write it in a different color. You could set it off on the side, but you want to write it neat, and you want to write it like step by step so that you can refer back to this until you've got this system down. Oops, that's not what we want. We want this. So the first step is this, and I'm going to have you do some stuff on your periodic table as we do this. The first step is this, that the positive ion, which is called the cation ion, comes first. And I'll show you how to figure that out here. So that's the first step you want to get down in there, is that write the symbol of the cation ion first. And the cation ion is the positive one. And right now you're thinking to yourself, how do I know what's positive and what's negative? Or hopefully you're thinking to yourself. Not the protons. And the anion? Yeah. So here's how you figure this out. On your periodic table that you've got in front of you right now, we kind of set it up with lithium, or potassium, right, when we looked at that. Everything in potassium's column has the same number of valence electrons, correct? So in order to be stable, they're all going to do exactly the same thing that potassium did. What did potassium do to become stable? It lost 1 electron. And when it lost 1 electron, what charge did it have? Positive 1. So on top of your periodic table, on top of that first column, the one that's got lithium, sodium, potassium in it, you're going to write a +1 on top of that column. Because everything in that column, when it bonds, is going to have a +1 charge, because everything in that column is going to lose. Yep, right at the very top there. Next column over, so Chris, on top of that thing on your periodic table, you're going to put a +1. Please and thank you. So the next one over, on top of beryllium, those things have how many valence electrons on the outside? 2. Easier to gain 6 or lose 2? Lose 2. If you lose 2, what's your charge going to be? Positive 2. So on top of the beryllium column, would you put a +2 for me? Next column we've got is boron. That's the next one over. That's got 3 on the outside. Easier to gain 5 or lose 3? Lose 3. If you lose 3, what charge do you have? Positive 3. So on top of that boron column, you're going to put a positive 3. Carbon's the weird one because they're at 4, right? So they can either gain or lose 4. So you can put plus or negative 4 on that. Plus/-4 because it can do either or. After that, going down for nitrogen. Nitrogen's got 5 on the outside. Easier to gain 3 or lose 5? Gain 3. So if you gain 3, what's your charge going to be? Negative 3. You picking up the pattern here? So oxygen should have what number on top of it? We just did nitrogen. Negative 3. Negative 3 on top of nitrogen. Oxygen should have a negative 2 because it's got 6, which means it's going to take on 2 more. And then the halogens have what number on them? Negative 1. Noble gain. Huh? That's halogens. We just did that one. Negative 1. So that's how you're going to know which one comes first because now you've got a list of what's positive and what's negative. And these things are always positive and negative. There's no mix-up between them. It's always one's positive, one's negative. So cation comes first, anion comes second. And we're running a little behind, so I apologize for that time-wise. So we're kind of rushing a little bit here. So next step, positive 1 first, negative 1 second. Next step here, do you guys know what lowest common multiple is? If you don't, I can clue you in. It is the lowest number that 2 numbers both multiply to evenly. For example, the lowest common multiple of 3 and 2 is 6, because that's the number they can both multiply to. The lowest common multiple of 2 and 2 is 2, because that's the lowest number that they can both multiply to. Lowest common multiple of 1 and 2? 2, because that's the number they can. So it's the lowest number that stuff can multiply to. We'll find it, and I'll walk you through how to do this. And then we'll do this last part here, which is take that number and divide it by the oxidation number to get your final answer. So I realize that is a lot here, and I'm trying not to rush you because I got us behind a little bit. But if we take a look, and I say we want to combine magnesium and chlorine together, when you look at those and write the formula out, magnesium is going to come first because if you look up there, it's in a plus column, and chlorine is going to come second because it's a negative, right? If you look at the top of magnesium, it's plus 2. You look at the top of chlorine, it's a minus 1. Positive 1 first, negative 1 second. Step 1 and 2 done. Find the lowest common multiple of their oxidation number. This is the only somewhat tricky part. Oxidation number of magnesium is plus 2. That's the number you wrote up there. Oxidation number of chlorine is minus 1. That's the number you wrote up there. Once they're in order, positive and negative, you don't have to worry about the positive and negative. What's the lowest common multiple of 2 and 1? 2. So LCM is equal to 2. From there, take that, divide it by the oxidation number, and that's how you get the number down here, the subscript. What's 2 divided by 2? 1. You don't have to write a 1. It's 2. What's 2 divided by 1?
2 divided by 1.
Yeah. So the formula for this is MgCl2, magnesium chloride. That's how you figure that out. Still waiting.